So my name's Dave Weston, better known, my friends call me D-Wizzle. There's a long story about that, something about a rap career, but I'm not going to talk about that here. Instead, I'm going to talk to you about the two jobs I have. The first job I have is I work as a research manager for Windows Defender Advanced Threat Protection. So my team investigates advanced threats, builds a lot of the detections and engineering capabilities in the product. So we focus on detecting bad guys in the morning. In the evening, I have another team who emulates the bad guys. So we write exploits, we write implants and malware, we innovate on new, different types of threat technologies as a way to emulate our own ATP team. So in that way, I have two teams that sort of battle each other. We actually call that process sparring, where one team is actually building attacks and the next team is trying to detect them. And so I'm going to talk to you a little bit about how we use that process to make sure that the emerging versions of Windows, by the time they get out the door, not only do they have the right prevention technologies built in, but they have the right detection and post-breach technologies. So most of you are probably familiar with a lot of the great prevention technologies that we have built into Windows. Examples of that are the device level protections we have. So we have device health attestation that will tell you about any tampering in the critical operating system components from the hardware, firmware, software, all the way up to the app level. We have device control and various security policies that allow you to integrate there, so that's great. We have multiple identity protection technologies, 2FA, Windows Hello, and biometrics. That hardens the credential, access, and authentication technologies associated with Windows. Even better, we've got information protection. So that's technologies like BitLocker, full disk encryption, enterprise data management, and other technologies that allow you to have control over that data layer of your operating system. And then finally, we have threat resistance. So built into Win 10, we have a machine learning technology called Smart Screen that applies reputation to both the apps that you download from the web, but as well as the URLs that you navigate to in browsers like Microsoft Edge and Internet Explorer. And then, of course, we have awesome technologies like Device Guard and exploit mitigations, Control Flow Guard, Return Flow Guard, all the different exploit mitigation technologies. Combining that with App Locker, we have a formidable system for threat prevention. And in fact, it's so good, we've had a number of people recognize it as potentially the most secure operating system out there. So up on the board there, I have two quotes from two Alexes that I respect greatly. The first is Alex Damos, the CSO from Facebook. He said, Windows 10 might be the most secure operating system on the planet. Alex Ionescu from CrowdStrike said, no, it is the best secure operating system. So across the board with these layered technologies and the story we put together, people are saying that threat prevention built into Windows is great. Now the question is threat prevention enough? What I would argue is we can see two examples from recent news. The first being the Trident exploit that targeted iOS 9.3. There was a 0-day in the wild targeting iOS. Additionally, there's a hacking team incident from about 2 years ago targeting Android. Both of these platforms, I think, stack up well against the best threat prevention technologies. Again, they have strong code integrity, they have great exploit preventions, numerous different protection mechanisms. However, when stuff goes wrong, there's not much there to detect, right? How do you get a detection for a potential breach on your iPhone or your Android phone in your pocket? There isn't much there. So what we've done in Windows is we've conceived of a very hardened platform with Windows 10, but we've also, in turn, built into our detection strategy and our layered defenses a post-breach detection solution that we call Windows Defender ATP. And the goal here is to not have to bet on prevention. Our motto is assume breach, assume the mindset that no matter how hardened the device is, that you're going to need to detect it. And so we've built a system that is that is complementary to our prevention technologies. Now, the question is how do you build a post-breach detection system into the operating system that does everything? Because the concept is detecting all things is hard. If you think about the forms a breach can take, it can go all the way from the simplest kind of phishing attack all the way up to, a multi-chain exploit 0-day. And so we also have the issue of it's not just malicious code that might get on the machine, but there's, of course, also humans who might do a pass-the-hash attack, but hands on keyboards. And so we need to be able to detect both deterministic code and dynamic humans equally. That's a big challenge. Additionally, with Windows in particular, we've constantly got new features. So this creators update we're about to ship, it's got numerous new features. we've got to be able to conceive of how they'll be attacked before we even ship it out to customers. We can't just wait for customers to get owned. We've got to do some work ourselves to conceive of the type of detections that we need to build to protect those components. And then finally, the gift and the curse of Windows from a detection standpoint is it's extremely popular, and we have lots of information coming in from all the Microsoft service. The other side of that coin is it's the most frequently attacked operating system on the planet, so we've got to be able to consume that information and make it actionable. So the question on the tip of our tongues, particularly when we're building Windows Defender Advanced Threat Protection, is how do we address and create a strong value proposition in our post-breach detection technology built into Windows that matches up to these challenges? And what we did is we looked at the success we had in the prevention space. So we've long had a mature process for analyzing attacks as they come into Windows to fix or mitigate issues. So this isn't on the detection side. This is purely for improving the durability of Windows. So every time a 0-day hits the wild, a new piece of malware, a new exploit technique, we have a comprehensive set of partners that will stream that information into us, and we break down those attacks into their core. The next thing we do is we get security engineers get their hands dirty. They work on new kinds of code or new innovative technologies that'll disrupt that attack. And finally, we've developed a process for actually attacking ourselves to test that that process works. So we analyze the exploits. We build what we think is a new prevention technology. The next question is, does it work? And so we've actually begun to employ world-class offensive security engineers, people who can build exploits, who have the talent to target these technologies to make sure that they can stand up to the high-threat environments in which customers will deploy them before we ship. And so this has been a very successful strategy for us. We've dropped significantly the number of exploits in the wild, particularly with Win 10. We've released a lot of statistics and news on that. So the question in our mind when we were releasing this post-breach system is, our hypothesis is, can we take the engineering and product truth and frankly, empirical data approach that we've used for building prevention technologies and apply it to post-breach? And we think we have the answer there. So our strategy is to make it very difficult and costly, not only to exploit or get malicious code or malicious control of a Windows 10 PC, but to evade our detections. And so, again, we strongly believe in our engineering chops. There's not a lot of magic boxes or waving hands here. I'm going to talk to you specifically about the types of tactics and engineering approaches we use to building detection in. So the first is we've got to be able to emulate attackers in a very forward-thinking way. We can't just look at the historical data. We've got to be able to invent new attacks and detect and prevent them before they hit customers. The next thing we need to be able to do is track all of the invariants, not all of the malware out there, not all the behavioral techniques, but the intrinsic attack techniques that we need to detect. We need to make an oracle of truth. And so that is a key strategy, is knowing your attacks is the first step into being able to detect them. The next thing we leverage is our OS as a sensor. So there's many folks here that are going to talk to you today about their detection techniques, et cetera, et cetera. And what we're doing inside of Windows is we're building into the very fabric of the operating system the ability to identify a data that is important for detecting attacks. And we're constantly expanding that just like any other Windows feature. And then finally, our main goal is to expose our analytics and our data to contain breaches. So breaches are going to happen in the modern world. It's an inevitability. The goal is making sure that that breach lasts a very short period of time and that attackers don't laterally move or expand into your network. And we do that by exposing data that's actionable for our customers. And so the first thing I'm going to do here is talk to you about what does it mean for us to track and prioritize these attack invariants. Well, the cool thing and the bad thing about being at Microsoft is we're one of the most targeted operating systems on the planet. So fortunately, because we have to fix many of the attacks, they actually come into us from various partners, customer sources, et cetera. We also have arguably the largest set of security telemetry of anyone. We own an email service, actually 3 of them. We own a search indexer. We've got multiple chat services. So all of those places are great sources of attack information that we can build together to synthesize new attack invariants that we want to stick into our oracle. And then, of course, there's classical threat intelligence exchange. There's internal data sources like red team operations. But our goal through this process is to build up the list of the superset of all the possible attacks we could detect so that we can compare it to what we actually detect and over time build up our KPIs. So if you think about knowing every attack possible is 100%, we want to strive to 100% coverage of those attacks as much as possible. But that means you have to know them, and beyond knowing them, you have to know what are the technical, specific invariants that need to be covered. So, just to give you an example of what this looks like in practice, I wanted to show you an example of our attack technique prioritization. So let's say that we were able to identify 3 invariant techniques. The first example might be something like a code injection technique. Create remote thread injection. It's a very common API that attackers will call to move laterally across processes in the system. Additionally, set thread context might be another way to do that. And finally, dumping LSAS credentials is a classical technique for credential theft. What we want to do when we're building a prioritization matrix of what to cover from a detection standpoint is we want to assign a priority to these detections, because the fact of the matter is there's billions of different attack techniques, and covering them all equally is not a great strategy. So instead, we want to focus on the things that actually matter. And we do this by assigning essentially a weight to the attack based on how often we see it in customer environments. Based on that weight, we'll prioritize building a detection, and finally, the data needs in the operating system. So using this process, we can move away from hand-waving and saying we cover all the threats, instead to building an engineering plan to covering the things that matter most. And we think long-term that this will be the special sauce. Microsoft has a brand for being quality and high engineering sort of IQ, and we want to take that into the detection space. So the outcome of this is that we are able to get a detection dictionary that spans the entire attacker kill chain, from the delivery mechanisms that it might be very common, things like child process creation, kernel exploit detection, across installation, persistence, exploration, etc. So our goal is to make sure that our detection dictionary covers at all times the highest priority threats and the things that matter the most based on our weighting scheme. And again, that's about moving away from hand-waving and saying we cover threats into an engineering and data-driven approach to building a detection library. So this next part of the talk, I want to talk to you about how we actually use red teams. So if you think about red teams and threat emulations, there's really 2 types. The first is what I'll call the classical red team, and that's an operational red team who will pretend to be an attacker, right? They might do a reconnaissance phase and enumerate your network. They'll identify potential holes coming in. Maybe that's a loose configuration, a low password policy, SQL injection, you name it. That's been around for about 25 years, and most folks know it well. We definitely leverage operational red teams. In fact, we think that our folks are innovating in tradecraft and new persistence, new lateral movement techniques all the time, constantly pushing our detection team. So we're not just dealing with a set of static reports from customers, we're actually creating new techniques to cover. The second thing we're doing is we are using software red teams to emulate what we think are the apex attackers. So what does a software red team do? Well, they find vulnerabilities in Windows from the browser, kernel, hypervisor, you name it, and they build actual exploits. So we're not just waiting for bad guys to create exploits, we create exploits ourselves to form the raw material for new detections. And in fact, I incentivize, as kind of the manager of both red and blue teams, I incentivize them to be almost, contradictory of each other. So if the red team guys can build and find a new exploit or technique that the blue team guys can't detect, that's kudos to them, and vice versa. So we create this sort of sparring session where you have almost 2 adversaries going at each other on a day-to-day basis, and we think over time that drives our capabilities far up, and something we release back to customers. So to take a case study of that, with Windows 10, Microsoft released what's arguably a pretty revolutionary feature in Device Guard. So Device Guard uses a hypervisor to create a secure enclave in which to store code integrity and credential policies, something that our high-value customers who have a high-threat environment will want to deploy. And one of the things we wanted to make sure before we ship that out the door is that it's resilient to an APT team. So what we actually did is we had our own APT team go and build not just one exploit, but multiple exploits, and we exploited it in the exact same way you would expect a nation-state adversary to do it. We did that multiple times until we ran out of techniques. And the outcome of that is actually particularly interesting. So in one part of the chain, we actually created a new exploit. And in the result were 2 proactive mitigations and detections. The first is because we built an exploit in this device guard scenario, we identified a new kernel exploit technique that we mitigated in the platform by creating a new check. We also followed that up with creating a new detection specifically for that technique and putting it in Defender ATP. And this was really a proof of concept for our new idea of using red teams to harden the platform. And the outcome, we would say, is a raging success. Back in October of 2016, a threat adversary we call Strontium used a kernel 0-day paired with a flash 0-day in the wild to attack multiple customers. Ironically, it was the exact same technique that our red team had built internally and pioneered. So we had an actual prevention for it because attackers tend to think alike, especially advanced attackers in that sense. So we had both a prevention and a detection story. So the latest version of Windows 10 was prevented the exploit in the wild from working. So I'm actually going to show you in practice how that looked. So this is a video of Strontium's exploit that we pulled from a threat intelligence source, actually operating on Windows Defender ATP. So this is actual browser-based exploit running a flash 0-day. We had to modify Windows to make this demo because it actually had a prevention technique built in, but I wanted to show you what it looks like in practice. So the flash exploits just run, and it redirects the user to the Politico website just to sort of redirect the interest of the user. What we can see in the ATP console is a suspicious PE file was dropped. That's a PE that's never been seen. A very uncommon binary was dropped by the attacker. It's part of their payload. And the integrity of the sandbox process went from very low, right, because the sandbox doesn't need much privilege on your system, all the way to a system-level process, which is indicative of a kernel exploit. And so these were detections that were built internally to detect our own red team that in practice worked perfectly against the entire exploit chain of a real targeted attack in a real 0-day in October of this year. And so we think this is a great proof of concept that our own muscle in the offensive space is translating into goodness for our customers. It didn't just stop there. We actually have what we call a one hunt exercise every year inside of Microsoft. And what we call that is a live adversary exercise. So we get a bunch of the offensive red teams across Microsoft to compete with the blue teams on our own network. And the goal here is to dog food our own network and make sure our detections and defensive mechanisms, our incident response mechanisms work well. And so my team, the software red team, or the offensive security research team, actually built an entire 0-day exploit chain to test at Microsoft. And the goal here was to make sure the stuff we built into Defender ATP and other detection systems would work in practice without prior notification against a real 0-day. And so the goal here was to take an internal website, compromise it, just like an attacker would, place an iframe on that website containing a brand new, never seen before 0-day. We actually did this in practice on the network. Have it connect back to an exploit server that would then return a second 0-day in the kernel and use that to connect back to a command and control service and operate just like real attackers would. So classic kind of watering hole attack. The difference is Microsoft built this 0-day in its own product to test itself to make sure our own detection and systems were there. So in this first video demo, I'm going to show you an actual 0-day exploit we created. It's been obviously patched and mitigated since then, but at the time it was a 0-day. So what you'll see here on the right is a bunch of spew, but what you're looking for is that the browser process is actually going to launch Notepad running at system level. So that's proof that we're able to compromise the kernel and clone our system token. So there you can see Notepad running at system. Now, we want to see that same 0-day attack. Again, no patches running on a detection system. And what we did here is not only did we run a 0-day, that would be too easy just to detect, but we actually made sure that the payload delivered by the 0-day never touched disks. So it's an in-memory payload only, and then did some other post-exploitation operations inside the kernel. And what we'll see is that the instrumentation and the advances we built into the creators update of Win 10 allowed us to get full visibility not only to one part of the chain, but to the entire chain from the zero-day exploit all the way up to a zero-day kernel exploit, as well as post-exploitation operations. So that first kind of scene there, we're running without kernel and memory sensors. In this second scene, we're running with new enhanced sensors based on this modeling exercise, and we can see process injection, and that's where we're moving laterally from the edge process into WinLogin, a system process with the system token. We can also see anomalies related to executable code creation, which we call indicators of successful exploitation. I'm going to talk about that in just a bit. But we can see all the indicators from start to finish, from the delivered browser exploit through the kernel and lateral movement. And this is only possible through the ability of doing offensive modeling. So the outcome there is that Microsoft built our own zero-day exploit in order to model advanced attackers and make sure that we were capable of detecting them. All of the information that we learned during that operation was built into the creator's update, specifically Defender ATP, as well as other mitigation technologies. And we think this is a capability that sets us apart from our competitors, in that we know the operating system the best. We're regularly innovating on the attacker side to drive our defense side. And in this final section, I'm going to talk to you a little bit about how we built that last demo. What are we doing in the operating system to make sure that we have the capability to detect some of these more sophisticated techniques? So the way I would characterize the attacker capability scale is in really 3 modes, although you could argue this is a much larger scale. The first is, your average attackers using very simplistic techniques. Maybe they social engineer a macro. They move laterally through systems using classic pass-the-hash techniques, commodity tools, and they persist using what we call auto-start entry points, or classical kind of tradecraft. Nothing fancy here. Unfortunately, works too often, but very classical, repeatable playbook. Those are easily detectable through file, process, and network primitives, because all of the activity that these attackers use are visible through those data forms. Now, advanced attackers realize that their victims have tooled up and have begun to deploy systems that are capable of seeing these invariants. And so as a response, they've in turn tooled up. They've started to develop zero-day exploits to use where macros and other social engineering forms are not possible. They've moved away from file or disk persistent implants into memory-only implants. They've moved away from social engineering elevation techniques like UAC bypasses, et cetera, into kernel exploits, and they use all custom tool chains. So the way we've responded in the creators update to those type of attackers are, we've built memory sensors to detect their implants. We've tooled up and made much more sophisticated and comprehensive cross-process injection sensors, which I'm going to talk about in a second. And we've built an unparalleled kernel sensor that's capable of detecting kernel exploits and a multitude of post-kernel exploit invariants in the kernel. Now, looking forward, we still believe there's a set of attackers beyond advanced, which we call Apex, truly the best of the best. And those attackers are invisible in most cases today. They often target firmware or other forms of embedded software where there are no sensors. Maybe they're using protocol or other logic-based attacks that are hard to detect with common network sensors. And that's where we're going long-term, is we've got our own Apex attacker team, and we are game theorying or learning those new techniques, and we're using that to innovate in our detection space. So talking about some of the invariants we built or detection techniques we built in the creators update, the first that I would talk about is cross-process injection. So cross-process injection is an absolutely key capability for attackers who want to persist in memory. They might want to move from process to impersonate that process's privileges or impersonate its access to particular data, network credentials, et cetera. Conventional detection systems generally would focus on 1 or 2 invariants, maybe create remote thread injection, write process memory, et cetera. There's been a lot of innovation both on the attacker side and the research community. You might have heard such buzzwords like the anti-bombing attack or QAPC, et cetera. What we did on the ATP side is we sat down with the kernel team who actually writes the code for all of these APIs, and we looked at the choke points that were possible comprehensively across Windows, and we built sensors that look at all of them. So we moved away from kind of a tit-for-tat, whack-a-mole to we essentially gated off that entire detection platform. So that's a critical new advancement that's available in the Creators Update, and it's allowed us to make sure that we're covering all of those cross-process detection techniques. And one of the alerts that you may see if you're running into a threat that uses something like this is process injected code into another process. That's our indicator of attack related to cross-process injection. Additionally, cross-process detection on its own is not sufficient. We also want to understand when the attacker injected code or ran an exploit that runs in memory. There's a very common technique available in most exploitation toolkits called reflective DLL loading. And that's just a fancy word for saying an executable was loaded in memory and never touched the disk. Now, generally, that's a difficult type of attack to detect. The only real option that you see in most solutions out there is the ability to scan memory. And that's back to kind of a pattern or content classification mechanism, which is pretty low on the durability scale. So what Microsoft did is we turned the problem on its head. Most of you are probably familiar with process reputation, the idea that you take a process that's never seen very often and you raise your risk level. If you see a process all the time, you lower your risk level. We took executable memory and built reputation algorithms on memory. So now when we see an anomalous memory exercise, a process that's acting very strange, we're capable of classifying its memory-only behavior in a way that's impenetrable from user mode and is implemented in the kernel itself. And using this, we believe that we're able to detect most common in-memory detection techniques, as well as some of the zero-day exploits in which we showed previously. So walking you through the previous attacks, here's just a quick screenshot to refresh you. In this particular case, you can see the cross-process injection and memory alerts related to that previous zero-day exploit. What we're able to see here with this second alert, indicators of successful exploitation have been observed is the actual exploit in the browser loaded a new DLL, which is a very large, what we call executable memory segment. That's quite anomalous for the profile of this app, so we're able to alert on that. Subsequently, after the kernel exploit runs, the attacker moves laterally away from the browser into a system-level process, and we catch that cross-process movement through our code injection instrumentation. So that's a pretty cool set of capabilities there. Now, we didn't just stop there. If you looked at my advanced attacker profile, one of the things you'll remember is that the kernel exploitation is a key capability. And so we cover kernel exploitation in Windows Defender ATP as part of the Win 10 Creators Update in a number of ways. First is we can detect invariant attacks related to post-exploitation. So when an attacker gets system-level or kernel-level code execution, there's a number of things they might want to achieve. If you have something like device guard employed, or if you have code signing turned on in your kernel, which is there in 64-bit by default, the attacker will want to disable code signing. We're able to observe that invariant activity in Defender ATP and alert on it. Similarly, often kernel exploits will want to steal the system token, so they might be running in a sandbox or other lower privilege token, and they want to be able to dump credentials, access sensitive data, etc. So I've got to elevate their privileges on the system. The most common way of doing that is simply stealing a token at the kernel level from a privileged process and sticking it into your unprivileged process. That is something that is comprehensively covered here in the new version of Defender ATP. And then finally, classical rootkits or implants that might want to hide in the kernel and observe system-wide activity, they'll often take control of various callback mechanisms or their key kind of choke points within the operating system. We monitor many of those and alert on anomalous activity. And so again, going back to my previous kernel exploit example, you can see in action our indicator of attack, our detection primitive for modification of the Windows kernel state. What this is showing us here is that actual kernel exploit running in real time and its behavior being detected by ATP. So in conclusion, we believe that we're evolving our post-breach detection centers, our post-breach detection capability and our sensors in concert with our prevention capabilities. So just like we're stacking up constantly and innovating in new exploit techniques, we're accompanying those with new detection sensors. So we're moving away from just userland into kernel mode. We're moving away from just kernel mode long-term to things like firmware. We're constantly pushing the bar with instrumenting the operating system to make sure we're on top of the latest attacks. And we're doing that by making sure that the very Windows developers who are writing that kernel code or the code integrity or even the firmware are sitting with our security engineers and collaborating and making sure this is part of the fabric of Windows. And then finally, our own attack capabilities are helping to drive forward by modeling that advanced and apex attacker mind state. So in conclusion, Microsoft has really built post-breach and detection into the very essence of the operating system. I think I proved the case with that first slide that Win 10 can compete from a prevention standpoint with anything on the market. The difference is your iPhone doesn't have a detection mechanism. The Chromebook doesn't have a detection mechanism. Microsoft takes a very realistic mindset and says, no matter what prevention technology you have there, breaches are going to happen, and our goal is to detect those breaches as quickly as possible and make them actionable. We're also using our same engineering mind state, less marketing, more engineering. We're focused on a data-driven strategy for evolving our post-breach detection, and we think that's going to give us remarkable results. Again, less marketing, more engineering. And finally, we're using our own substantial offensive capabilities to model the next generation of attackers. And with that, we think we've developed post-breach as a key part of the Windows security promise. So thanks very much for your time. If you have any questions, I'll be happy to take them offline.